Welcome back, everyone. Ready to dive into something pretty cutting edge? We're talking AI today, specifically a new way of building those supersized models, the ones tackling really complex problems.
Yeah, it's called ReMoE.
ReMoE. Okay.
It builds on this idea of mixture of experts or MoE, kind of like,
Like a team of specialists.
yeah. Instead of every expert weighing in on everything, you just consult the ones with, the right skills for the job.
Makes sense. Efficiency is key when you're dealing with these massive AI systems.
Absolutely. And the paper we're looking at today digs right into that.
Okay, which paper are we talking about?
It's called ReMoE, fully differentiable mixture of experts with ReLU routing. A team from Tsinghua University put this together, and they're tackling some real limitations in how traditional MoE models choose which experts to activate.
So how do these models normally make that decision then?
Well, the traditional way is called TopK routing.
Top K.
Yeah, it picks the top K experts based on which ones seem most relevant to the task. But the way it does this, it kind of creates these abrupt jumps in the model's calculations. Imagine a car suddenly switching gears not very smooth.
Yeah, I can see how that would be a problem.
Right, so this discontinuity, that's what they call it, makes top K routing really difficult to train.
Uh-huh.
And it also limits how big, how complex these MoE models can get.
Okay, so is that where ReMoE comes in?
Mm.
With a smoother approach?
You got it. It uses something called a ReLU function for routing instead of that top K.
ReLU, no, that sounds familiar. What is that again?
Think of it like a soft on-off switch for each of the experts. So instead of those sudden jumps, we get gradual transitions.
Oh, so if Top K is the car with the jerky gears?
Exactly. ReMoE is like a car with a continuously variable transmission, much smoother, much more efficient.
I like that analogy.
Yeah.
Okay, so ReMoE picks its experts smoothly.
Uh-huh.
But how does it make sure that it doesn't just activate all the experts all the time? Wouldn't that defeat the purpose of having specialized ones?
That's a great question. And that's where the really clever stuff comes in. There are two mechanisms at play here. The first one is called adaptive L1 regularization.
Adaptive L1 regularization. All right, break that down for me.
Basically, it means ReMoE penalizes itself if it tries to use too many experts at once, like a budget for your expert consultations.
So it keeps the model from being too greedy with its resources.
Yeah, exactly. And then there's this second mechanism called load balancing refinement.
Load balancing. Okay, I'm intrigued.
This one makes sure no single expert gets overworked, spreads the workload evenly.
Oh, so it's like a project manager making sure everyone on the team is pulling their weight.
Exactly. Keeps everything running smoothly and efficiently.
That makes a lot of sense. So not only is ReMoE choosing the right experts, it's also making sure they're all working together effectively.
Precisely.
And I'm looking at figure 4 in this paper. It shows these 3 stages in ReMoE's training process.
Yeah, it's kind of like an apprenticeship program. In the beginning, we call this the dense stage. ReMoE activates most of its experts and lets them all learn a wide range of skills.
So everyone gets a chance to try everything out.
Exactly. Then as training goes on, we move into the sparsifying stage. And this is where things get interesting. It starts to prune down the number of active experts, encourages them to specialize.
Okay, so it's getting more selective, focusing on its strengths.
Right. And then finally, we hit the sparse stage. Now the model is running super efficiently with this refined set of experts, each one highly specialized in its own little area.
So the model starts broad, narrows its focus, and then settles into this lean, mean expert machine.
You got it.
I love it. So ReMoE has this smoother way of picking experts. It keeps things efficient, and it even learns and adapts over time.
Uh-huh.
Very impressive. Now, how does this all translate into actual performance? How does ReMoE stack up against the traditional MoE models?
Well, that's what we'll be looking at next.
I can't wait. Stick around, everyone.
Welcome back. So before the break, we were talking about how ReMoE actually performs, compared to those traditional MoE models.
Yes, smoother routing, those efficiency mechanisms, but do they really lead to better results?
Well, the paper dives into some pretty exciting findings.
Okay, what kind of findings are we talking about?
So they highlight figures 6 and 9 specifically, and these really show how ReMoE consistently outperforms that traditional approach across different tests.
Different tests. Can you give me an idea of what those look like?
One of the big things they found is that ReMoE just keeps getting better as the model size grows. Those traditional MoE models, they struggle to stay efficient as things get larger and more complex, but ReMoE scales up much more gracefully.
So bigger challenge, bigger advantage for ReMoE.
That's what it looks like. Another interesting thing, it also excels in something they call fine-grained MoE.
Fine-grained MoE. What's that?
So it's where the experts are like subdivided even further, even more specialization within the model.
Oh, so like teams within teams of
Uh-huh.
experts.
Yeah, and the tests show WUMO can handle this kind of complexity without sacrificing performance at all. Really shows how effective those routing and sparsity mechanisms are.
Speaking of sparsity, I'm curious how ReMoE keeps that balance, activating enough experts to get the job done, but not so many that it becomes inefficient.
Right, so you're asking about how it manages that proportion of experts that are inactive at any given time.
Yeah, like what's the sweet spot?
Well, it turns out this balancing act is crucial for preventing something called routing collapse.
Rotting collapse. Okay, that sounds ominous. What is that exactly?
It's when the model's routing kind of gets stuck, it becomes overly reliant on a particular expert or set of experts, ignores all the others.
Oh, so it's like a company that always assigns every project to the same employee, even though they have a whole team with diverse skills.
Yeah, great analogy. And routing collapse, it can really cripple the model's ability to use that full range of expertise it has available.
So how does remote stop this from happening?
They built a load balancing mechanism right into that L1 regularization scheme we talked about earlier. Make sure the workload is spread evenly across all the experts. No one becomes a bottleneck.
Back to that project manager analogy again. Everyone pulling their weight, nobody burning out.
Yep. And figure 8 in the paper actually shows this in action, even without explicit load balancing. ReMoE does pretty well because of that smooth ReLU routing, but add load balancing into the mix and the work distribution becomes much more even.
I'm looking at figure AG now. It shows the sparsity levels across different layers of the model.
Hmm.
Is this important too?
It is different layers in a neural network. They capture different levels of abstraction. The earlier layers are focused on those basic features, while the deeper layers handle more complex information.
Okay.
So by regulating sparsity across these layers, ReMoE can adjust its overall complexity to fit the task.
It's like a chef using different levels of heat to cook different parts of a meal. High heat to sear a steak, but lower heat to simmer a sauce.
That's a great way to put it. ReMoE's dynamically adjusting its level of complexity to get the best results.
This is all very impressive, but it's getting a bit abstract for me.
Sure.
Can we bring it back down to earth a little?
Yeah.
Talk about some concrete examples of how remote excels in practice.
Absolutely. One area where it really shines is handling massive amounts of data.
That's becoming increasingly important these days, right? With the explosion of data we're seeing in every field.
Yeah, traditional MoE models, they often hit a wall when you try to scale them up to handle those kinds of data sets. But ReMoE, with those routing and sparsity mechanisms, it can stay efficient even as the data size grows exponentially.
So it's like comparing a small local bookstore to a massive online retailer. The bookstore might have a curated selection, but it can't compete with the sheer volume and diversity of a platform like Amazon.
And just like Amazon's algorithms can recommend products from a catalog of millions of items, ReMoE can sift through mountains of data to find the relevant information and make those accurate predictions.
That's a powerful image. What about those fine-grained tasks we mentioned before? Can you give an example of where ReMo would be especially useful there?
Sure, think about something like language translation. Let's say you need to translate a really technical document like a scientific paper or a legal contract. Traditional MoE models might struggle with the specific vocabulary and nuances in those areas,
Yeah.
but ReMoE, with its fine-grained expertise, it can capture those details with much higher accuracy.
So it's like having a team of translators who are not only fluent in the languages, but also have deep knowledge of the subject matter.
Exactly. It makes a huge difference in the quality of the translation.
It does. So remote is all about bringing the right kind of expertise to the table, no matter how specialized or nuanced the problem is.
That's a great way to put it.
Now, as impressive as remote sounds, there must be situations where it's not the ideal solution, right? Are there any limitations to this approach?
Of course, no single model is perfect for every situation.
What are some of the things we should keep in mind then when we're thinking about remote?
One potential limitation is the computational cost. Even though it's designed for efficiency, training, and deploying a model with a ton of experts, it still needs serious computing power.
Right, so not something you can run on your smartphone.
Probably not. For certain applications, especially if you're working with limited resources, simpler models might be a better choice.
So it's a trade-off between power and practicality.
Exactly.
Any other limitations to consider?
Another thing to keep in mind is the interpretability of the model. As ReMoE gets more complex and specialized, it can become harder to understand how it's making those decisions.
So even if it's giving us accurate predictions, we might not always understand the reasoning behind them.
That's right. In some fields like healthcare or finance, where explainability is absolutely crucial, this lack of transparency could be a problem.
Interesting. It sounds like ReMoE raises some important questions about the balance between performance and interpretability in AI. But let's take a step back for a moment. What makes ReMoE truly groundbreaking? What sets it apart from other attempts to build these dynamic, specialized AI models?
I think it's the way it brings together all these key innovations. It's not just the ReLU routing or the adaptive L1 regularization or the load balancing. It's how those pieces work together. They're also beautifully integrated to create this model that's powerful, efficient, specialized, and adaptable.
So it's the whole package that makes ReMoE so special.
I think that's a good way to put it.
We've covered a lot of ground today. We talked about ReMoE's architecture, its performance, even some of its limitations. What are some key takeaways you hope our listeners are walking away with?
So we've been digging into ReMoE, this new way of building AI models that use these specialized experts.
But
And we've seen how it's more efficient, it can handle bigger challenges, and we talked about some of its potential uses.
yeah, and those performance gains shown in the paper, they're pretty remarkable.
They really are. So what are the big takeaways here? What makes
Yeah.
ReMoE stand out as like a major step forward in AI? Well, one thing that really struck me is how ReMoE might change the way we think about building these models in the first place. It moves away from that idea of a single massive neural network, and it really embraces this concept of a team of experts working together, you know?
Yeah, it's like going from a one-size-fits-all solution to something much more tailored, much more adaptable.
And that adaptability is key. We saw how ReMoE adjusts its complexity based on the task, and how it can even specialize in different types of data, like code or language.
It's almost like it develops its own internal division of labor, figures out which expert is best suited for what.
And it does all of this while staying remarkably efficient. Those mechanisms for sparsity and load balancing, they seem to be really paying off.
So it's not just a theoretical improvement, it's actually delivering results.
Definitely. It seems like ReMoE could be a real game changer, especially for certain applications.
Right, like the ones dealing with huge data sets or tasks that need that high level of specialization.
And this is really just the beginning. I'm excited to see how researchers keep building on this foundation, exploring new uses for ReMoE.
This has been a fascinating look at ReMoE. Thanks for guiding us through it.
My pleasure. Always fun to dive into these cutting edge
And
topics.
for all of you listening, thanks for joining us on this deep dive into the world of AI. We'll catch you next time.